we will be talking about prime factorization today and simplifying square roots. Is there anyone else who needs a piece of paper to take notes on? So I do label the notes. You'll notice I say 1 dash prime factorization. That's because we're notes 1. They'll correspond with assignment 1. So you know what goes together and so you can keep things organized. And I do want you to put the date on your notes as well, because that's another way to keep things organized. So today we're talking about prime factorization and simplifying square roots. So every day I tell you the topic and I tell you the goal. I also write it over here on the whiteboard so you can see what we're doing before class or even what we're doing next time. So our goal today, our objective, that's another word for goal. Does anyone know what SWABAT stands for? Students will be able to. Students will be able to. You'll see a lot of teachers use SWABAT. But when you see the SWBAT, that just means students will be able to write a number in prime factorization form and write a radical in simplest form. So we have 2 goals today. Prime factorization you've probably seen before. And if you can do your division and multiplication, it can be a pretty easy process. Writing a radical in simplest form, you may have also seen before, but with both of these, we're going to try and take them to a more complicated level than you have seen before. So in order to accomplish our goal today, we need to know a few vocabulary words because I'll be saying these words a lot today. I'm going to pause for a second while everyone catches up to the objective. So we have 3 vocabulary words today. Our first one is prime number. Our second one is radical. And our third one will be integer. I'm not showing it yet again so that everybody gets a chance to finish writing down the objective. So our first one is prime number. The second one is radical. The third vocabulary word will be integer. So really quick, I want you to discuss with your table and see if you know the definitions already for any of these words. So I'm going to give you just 1 minute, and you need to be talking to the people at your table, not back. So talk to the people at your table about the definitions for these words if you recognize them. You have 1 minute. More seconds. You guys recognize anything? It sounds vaguely like 21. General. let's refocus. Prime number. Did anyone recognize prime number? What did your table say a prime number was?
I don't know.
Okay.
It's a number that it can only you can only get to it by adding it by itself, right? Or like by
Okay.
one, I mean.
Yes. Okay. But instead of adding, what should we be doing?
Multiplying.
Multiplying. Okay. So, where did I put my notes? There we go. This way I read it the same way every time. So a prime number, or a number, sorry, well, I already started writing it. I'm not going to change it. Is a number whose multiples or whose factors are 1 and the number itself. So Silky's table was correct. A number whose factors are 1 and the number itself. Okay? So here's an example of a number that's not prime. 6 is not prime. Why would 6 not be prime?
You can times 3 by 2 and get it.
You can times 3 by 2 and make 6. You still can multiply 1 times 6 and make 6, but it has a second option. So let's talk about a number that is prime. 11 is prime. Why is 11 prime?
7 is prime.
You can only get to it by times.
You can only get to it by timesing 1 times 11. And Silky was right again, 7 is prime. What are some other prime numbers? 3, 5, 13.
1, 50.
Okay, that's actually a misconception. 1 is not prime. I actually didn't know this until just a few years ago. It's something that is often commonly misconstrued. 1 is not prime. Okay, and here's why. It said the definition is the numbers whose factors are 1 and the number itself. So we could write 1 as 1 times 1, which would make us think, hey, this is prime. But I could also write times 1 again. Is that still 1?
Yes.
But does it follow our definition?
No.
No, because our definition only has 1 and the number itself. Now we have 3 numbers instead of 2. And I could keep doing that. I could keep writing this. So 1 is not technically prime. What's the only even prime number, though? I haven't heard that one yet. There's only one even
2.
prime number. 2. Okay? So those are the basic prime numbers you need to know. 2, 3, 5, 7, 11, 13, 17. There's a lot after that, but those are the ones we mostly work with. And we hardly ever see 17 or above. Okay. Radical. Did anyone recognize what a radical is? This one's a little bit harder.
It's gnarly, dude.
It does remind me, I always think Teenage Mutant Ninja Turtles, but that might be a little old school for you guys. Okay? So mathematically, radical means a square root. It's our fancy math term for square root. Just like instead of saying multiply, sometimes we say product. Sometimes instead of saying divide, we say quotient. It's our fancy math term for square root. And when we look at a square root, what is the square root of 36? What are we trying to say? 6. You guys are both correct. Because 6 times 6 is 36. This because part is very important for one of the things we do later today.
What's the square root of 68?
Okay, that one is not an exact. Square root of 64 is 8. Square root of 81 is 9. So square root of 68 would be like 8.3 something, 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 something. And it goes forever. We can't write it as an exact decimal. like square root of 68 would be 8.3 dot 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 forever. And that's actually going to be another important thing we talk about when we get to simplifying square roots. The fact that this and this are not quite the same thing. Okay. What about an integer? What's an integer? So our integers have to do with our whole numbers. What do I mean by a whole number?
Not like point something, but like just 1, 2, 3, you know what I'm saying?
Yeah.
Like not like 1.7 or 1 point, no,
Yeah.
just a whole number, yeah.
Good. So no decimals, no fractions, just your basic counting numbers. 1, 2, 3, dot, dot, dot. Okay, but integers include more than just those whole numbers. We could also include 0. 0 is considered an integer, but it's not considered a whole number. And then our negative whole numbers. Those are all considered integers. And I will use that term a lot. So let's talk about the process of prime factorization now. So prime factorization, like I said, it may be something you have seen before. And it's very dependent on knowing our multiplication tables and knowing what divides into a number and things like that. Jorge, keep your head off your desk, please. So prime factorization is the process of rewriting a number as the multiplication of primes. So when we find the prime factorization of a number, we're just trying to find all the prime numbers that multiplied together make the original number we had. So for example, our goal is write 28 as 2 times 2 times 7. So I gave you the problem, 28. We're going to do the prime factorization of that. And the answer, 2 times 2 times 7. We just need to know how to get there now. And we want to know, why are we even doing this? Why write 28 as 2 times 2 times 7? So the reason we want to write 28 as 2 times 2 times 7 is because prime numbers are special. They have special properties that make it so we can do some things mathematically that we couldn't do with, this is called a composite number with 28. Composite is just anything that's not prime. Okay, so the reason why is because prime numbers are special, so it makes it easier, not in all cases, but for what we're going to do later today, especially, it makes our life easier. So, our example is that we're starting with 28. And now we need to just know how to get to writing it as 2 times 2 times 7. So we know we want to write this as multiplication, so let's take 28 and write it as a multiplication problem. What are two numbers that multiply to be 28? 4 times 7. The only problem with that is not all of the numbers here are prime. We have 4, and 7. Which one's not prime?
7.
Which one's not prime?
4.
4. Okay. So I need to split 4 up because it wasn't prime. So now I say, do I have only prime numbers? And since I split 4 up, I don't need it anymore. It's not part of my problem once I've used it. So now we have a 2, a 2, and a 7. Are those all prime numbers? Yes. So we write our final answer as 2 times 2 times 7. So that was our most basic type of example. I'm going to have you guys work with your table to try 3 other prime factorization problems. And they're all just a little bit different so that we can see all the types of problems that might come up on the homework. So I will give you 3 minutes to work with your group to find the prime factorization of these 3 different problems. These are 3 different problems. So I need everyone's attention up front. The first one would need my seating chart to try and get names down. That's why I have you in a seating chart. Danny, right? Will you tell me what your table did?
-5 times 3.
-5 times 3. Does anyone have a different answer?
-3 times 5.
Okay, we could have -3 times 5. We could have 5 times -3. So these can all be written in slightly different ways and still be correct. Either one works. Both are considered correct. What about 7? Colton, tell me what your table did for 7. Nothing. 7's prime already. That one we get to just say, hey, 7's prime. I did see some people write 7 times 1. What's wrong with that?
1 is prime.
1 is not prime. Okay. I know it seems like it's prime, but it's not. And then 180. Adam, what did your table do for 180?
We did 2 times 2, then times 3, and then times 3, and then 5.
So that's your final answer. 2 times 2 times 3 times 3 times 5.
Yeah.
What did any table start with? What did someone start with? 18 and 10. Did anyone start with a different set of numbers? 90 times 2. Anyone start with something different? I saw some other people. There's a couple more ways. What else could we have started with? You guys are very quiet. There's at least 2 other ways. We did 18 times 10. We said 90 times 2. What? 45 times 4. Power?
30 times 60.
30 times 6. And 60 times 3. There's also 5 times, and I don't know what the other factor is, whatever 180 divided by 5 is. So you could have started this a lot of different ways. Doesn't mean you're wrong. Just means you're starting differently, but you should still get the same answer. So 18 is 2 times 9. 9 is 3 times 3. 10 is 2 times 5. If it helps, cross out the ones that are not on the ends of the branches because we don't use those. Remember, your answer should only consist of prime numbers. And I do want you to write your answer like that. Don't just show me the factor tree. Show me you know what your answer looks like. So the last thing we need to talk about with prime factorization is what to do if our prime factorization includes variables. It's not really that much different. The only thing we need to know about is what do we really mean by x squared? I heard it over here. I don't know. X times x. X squared is saying multiply x by itself 2 times. If I said x to the third, it would be x times x times x. If I said x to the fourth, it would be x times x times x times x. Okay, so that number up above is just telling us how many times we multiply. So when we do our prime factorization for this, with our integer and our variables, we start the same way. We still just focus on the integer first. This is where we start. Prime factorization of 20. So we just need 2 numbers that multiply to be 20. So under 2 numbers that multiply to be 20.
10 and 2.
10 and 2. Anything else?
5 and 4.
5 and 4. Either one works. We'll start with 10 and 2. And then we can factor 10 again. So for our integer, we get the prime factorization of 2 times 2 times 5. And now we just have to write out our variables beside it. We said x squared is really x times x. So we have times x, times x. And then y, it didn't have an exponent. So we just leave one of them. So this would be our final answer, including variables. So now we've accomplished our goal of prime factorization. We know how to find the prime factorization of a number. We figure out what multiplies into it and keep figuring out factors until we have only prime numbers left. So next, we want to try to simplify a radical. Once again, we want to know, why are we even doing this? What's the point of simplifying a radical? So our goal is to take a radical, like square root of 20, and write it as 2 square root 5. So we want to keep these in what's called exact form. Someone earlier said, well, what's the square root of 68? So let's plug this into a calculator and find out for sure what the calculator says. Okay. That was close. Square root of 68 is 8.246211251. And then the calculator stops. But that doesn't mean the numbers stop. It's just that your calculator can only show so many. Well, that's a problem, and here's why. So what I relate it to is my husband, who's an engineer. He works with gold mines. He builds gold mines. And in that process of building a gold mine, when you try and so gold doesn't just come in nuggets anymore. You don't just find a piece of gold on the ground.
It comes in like grams, doesn't it?
Well, once they refine it. But when you first see it, then, yeah, there's just a big pile of rocks, and there's like, for a ton of rocks, there's only like an ounce of gold. So you can't actually physically see the gold in the rocks even. So they take all these rocks and they pour a whole bunch of poisonous chemicals on them. They use like cyanide, they use mercury, they use all sorts of things that are not good for you. And it takes the gold and it bonds to the gold and it liquefies the rocks, so you get the gold out of the rocks. So with these poisonous chemicals, we don't want the leftovers, once they get the chemicals off of the gold, we don't want them to go into our water system, we don't want them to go into our air, because that would be bad for us. These chemicals can kill us and cause birth defects, things like that. So one of my husband's job with the gold mines is to make sure that the mercury that is released by this process gets, they call it scrubbing, gets taken out so that the air that's actually released, you know, you see all the industrial things with pipes and stuff going into the air. They have to have only 0.00001% of the mercury go into the air. That's the acceptable amount set by the government. That's a pretty accurate amount. You have to be very, very accurate to get it to look like this. So we can't use this decimal because this decimal is not accurate enough. It's an approximation. We need the exact form. Okay? Because if you start using the approximations, the more you use it in a calculation, it makes everything get off. So if you start with an approximation at the beginning, by the end, when you've done a long calculation, you're way off. So you want to be as exact as possible. So one of the reasons we want to do this is we want exact numbers. That's the first reason. We have to keep things exact so that when we actually go apply this to some real life situation, we can keep it as exact as possible until the end, when then you have to kind of round and take just a piece of the number. Okay. So that's our first goal. But square root of 20 is exact. Why do we need to take it to 2 square root 5? Well, square root of 20 is a bigger number, and I know it's not that much bigger, but we practice with small numbers. If we had like square root of 7,480, that's a big number to work with. We want to work with as small of integers as possible. So our second goal is not just to have exact numbers, but we want smaller integers. Because then it's easier for us to work with. Smaller numbers are easier to work with than larger numbers. So that's why we're doing this process. So once again, we have our start, square root of 20. We have our answer, 2 square root 5. Now we just need to know, how do we get there? So we start by finding the prime factorization. Of the number inside the radical. So don't write this part down, but just to show you, I could start with a number out here. I could say 5 square root 20. But we're only going to find the prime factorization of 20.
Is it cool if I move to the back?
Are there any seats in the back?
I meant like paper.
Oh, yeah. Yeah, that's fine. I don't care. You can use both sides. Okay. So, when we do our first step is only applying to the number under the square root. If there's a number outside, it is not part of this first step. So we do our prime factorization. We've already did the prime factorization of 20 in one of our other examples. We found two numbers that multiply to be 20. We did 10 and 2 before. Let's do 5 and 4 this time, just to show both ways. Which of those numbers is prime? 5. Sorry.
Mario, baby.
Nope.
That's
Zelda.
oh, okay. I like your style.
Let me turn off my sound really quick so that does not happen again. Sorry about that. And if that ever happens, that's something I won't take your cell phone for. Just turn your sound off, put your cell phone back away. Okay, we did 5 times 4. We said 5 is prime, which means we need to keep factoring 4. So now we write our prime factorization. We have 2 times 2 times 5. Okay, our second step, find any pairs. Once again, we only consider the pairs that are inside the square root. What set of pairs do we have for this problem? 2 times 2. Okay, there's our set of pairs. We've done step 2. Now step 3 is the weirdest one. Step 1, step 2, pretty easy. Step 3, a little bit weird. So we have to think back to what we learned about our square roots. We said square root of 36 is 6, and we said the reason that it was this way is because 6 times 6 is 36. So we had a pair here, but how many of these came as part of our answer? Just 1. So 1 moved out to be our answer, 1 just went away. We're going to do that same process, but we have an extra number involved. Now we have this extra 5 involved. But it's the same idea with the pairs. One of them will move outside to become our answer. One of them is going to go away. Because that's what a square root does. When you have a pair, it takes one outside and it gets rid of the other one. But the 5 is left over. It stays inside. It didn't have a pair for that process to happen to. So I tell a little story. It has nothing to do with math, but it just helps us remember this process. If you can't remember the why, we take one out, why we get rid of one. This story will help you just remember how to do it. So here's the story. The radical, this is prison. These guys are all stuck in prison. 2, 2, and 5, they're all in prison. So these two, they decide, hey, I want to bust out of prison. But one of them has an evil plan. His evil plan is when they're busting out of prison, he just has to be faster than the other guy. Because if he's faster, when the guards shoot at him, the other guy's going to get hit and not him because he's faster. So, as they're breaking out, just go with it. As they're breaking out, one guy makes it outside, but the other guy gets killed trying to escape. Okay? But the 5, he didn't have a guy to plan a breakout with. He couldn't have some other guy die for him, so he's stuck inside prison. Okay? So, stupid little story, just to help us remember the process. So, step 3, we've done it already, but let's write it out. We put 1 from the pair outside, and we kill the other. We leave any non-pairs inside. So once again, I'm going to have you guys try a couple of variations. Again, we did the basic type to show you how to do this, but there can be variations on this. So I'm going to show 5 different variations, and I'm going to assign each table to do just one of the 5 problems, and then we'll talk about all 5 together as a class. So we're going to ignore that one. We're just going to go to these ones. So, as you're doing these problems, consider what's different about the problem than what we did originally, and how do you deal with that as you simplify this. So problem 1, I'm going to assign this front table problem 1. Problem 2, problem 3, problem 4, problem 5. Then we start over. Problem 1, problem 2, problem 3, problem 4, problem 5. I would suggest writing all of them because when you get to the homework, if you have all these different variations in your notes, you can go check and see, well, what did we do with a similar problem? Yeah. Okay, let's talk about these 5 problems. So problem 1, what did you guys get for your final answer? What did you put for your final?
Actually, not.
2 times 2 times 2 times 3.
Okay. So that was part of your prime factorization. Okay, what about the other group? What did you guys get for your final answer?
6 and then 7.
Okay. So let's go through this now and see what we should do. On number 1, what's different about this problem? I still have a little too much chatting. If we could quiet down. Number 1, what's different about this problem than the one we did? There's different numbers for sure, but we still have a radical symbol. We still have a number under the radical symbol. So what specifically is different? Okay, what number? 3. Why is 3 different? It's in front instead of under. Okay. So our first step said to find the prime factorization of the number under the square root. So we only want to do the prime factorization of 28. So what are 2 numbers that multiply to be 28? 7 times 4. And then 4 will be 2 times 2. So at this point, we still have this 3, and we have our prime factorization of 2 times 2 times 7. So far, we haven't done a whole lot different. Just we had to take into account the 3. So what's our pair for this problem? The 2. So now is where we get something a little bit different. When we take one out, what did your group do? Hold on. Sophia? What did your group do with the 3 and the 2 we took outside?
We multiplied it.
We multiplied it. Okay? When there's already a number outside, we multiply. 3 times 2 is 6. And then we leave the 7. Okay, so there's our first one. The second one, the only thing that's different about the second one, what's different about the second one from the first one? There's a negative. You're still going to do the exact same process, but when you multiply, what did you guys get as your final answer? Diana, what did your table get? How far did you get? Okay, so you got that this was 9, 5. Did you get any further past that? Okay. What about 1, 2, 3, 4, 5, 1, 2? What did your table get as your final answer for number 2?
7 square root 3 times 5.
Okay.
Is that right?
There's 2 mistakes in it. You're close and I can see how you got it, but we need to be a little more particular. Okay, so we do have a good start. 9 times 5. What should we do next? Break down the 9. 3 times 3. So we have negative 4 square root of 3 times 3 times 5. Okay, so how do you think this became a 7? Where do you think that came from? They probably added the
Oh.
3 and 4, but what should we do instead?
Multiply.
We should multiply instead. So, instead of 7, we should have done, with our pair, the one we bring out, multiply -4 times 3. Okay. So now let's identify a second thing. What's wrong about this here? You're supposed to kill a number off. So we shouldn't leave that second 3 behind. But we do leave the 5. Okay? So we were really close. And those are some common mistakes that it's good for you to see. You saw that quite often, sometimes we add instead of multiply. It's a good thing to see because now you know to avoid it. Second thing that's a common thing. Sometimes you leave the number instead of getting rid of it. Now you know to make sure to get rid of that number, that second number in the pair. Number 3. What did your group get?
4 square root 6.
4 square root 6. What about 1, 2, 3, 4, 5, 1, 2, 3? You got that as well, okay? 2 groups got the same thing. That means we're probably correct. So when we did this, we do our prime factorization of 24. I'm going to skip the actual factorization part because we've practiced that a lot. So what do you get for the prime factorization of 24?
3 times 2 times 2.
Okay, so we find our pair. What's our pair on this one? 2 and 2. Now, what's different about this one, we have an extra 2. Does that matter? No. It's not part of our pair. It doesn't become one of the things we take outside. So we still take one outside and kill the other off. So we have 2 times 2 is 4. How did we get the 6 in this problem?
3 times
We just multiplied the numbers that were left over back together. Jaden, are you playing with the cell phone? Or?
I use my belt.
Okay. Anytime someone's just looking under their desk, it's hard to tell. Okay. Number 4. Noah, what did your group get as your answer?
We got 6.
6. What about your group, right? What did you guys get? 6 as well. Once again, seems like that's our answer. What's weird about our answer compared with all the rest? Just a whole number. There's no square root anymore. Okay? That is possible to happen. So, we break down our 9. 3 times 3. We have a pair. Kill one off. Multiply the other. 2 times 3 is 6. And there was no numbers left. We had 6 outside with nothing here. When that happens, we just get rid of the square root. If there's nothing written under there, it disappears. So your final answer will be 6. And then question 5. Yeah. Your group, right? What did you guys do? Okay, what about you guys?
Got 2 and 11.
Okay. Why didn't we do anything on this problem? 11 is prime. Okay, so we leave it. So the last thing we need to talk about really quickly, and then I'll hand out your assignment. Square root of 60x squared y. What's different about this problem? It's bigger and it's got an x and a y. It's got some variables. So we still start the same process. The instructions are still the same. We still need to find our prime factorization. So 60, what are some numbers that multiply to be 60? 10 and 6. We could have used 5 and 12,
30 and 2.
30 and 2. We could have used 4 and 15. Yeah. So there is a lot of options. Most people said 10 and 6 though, so we'll stick with that. 10 is 2 times 5, and 6 is 2 times 3. So then we have to write our prime factorization all the way out, including our variables. This was the last thing we talked about with prime factorization, is what to do with our variables. We have 2 times 2 times 3 times 5. What do I write for the letters?
Times X
Times x times x times
Y.
y. Good. So I still circle my pairs, even if my pairs are variables. It still follows the same process. So we have that pair. What's our other pair? The x's. So both of these have something come outside. We kill the other one off. And you don't have to write the arrows to the outside. It's just to show you what I'm doing in your notes. But you don't have to write the arrows for the assignment. So we have 2 and x outside. What's left under the square root?
3 times X. No, 3 times Y.
3 times?
5 times
5 times y. But I heard someone say the answer I want you to write. What can we do with the 3 and the 5? Times it. So 15y. Good. Normally we'll have time at the end of class for you to work, like 15, 20 minutes at least. Today, since we had to do the disclosure, you won't have as much time to work at the end of class.